There is a photograph of the universe taken when it was 380,000 years old. It is called the cosmic microwave background, and it shows the universe at the moment it became transparent, the moment light finally broke free and began to travel. But this photograph is not the beginning of the story. Before this moment, for 100 million years, the universe existed in a state so strange that shadows were impossible. Not because there was no light, there was light, billions upon billions of photons, but because there was nothing for light to do. No stars to illuminate, no planets to cast darkness upon, no surfaces for photons to bounce from. Just an ocean of hydrogen, cooling slowly in the void, holding its breath before the first star ignited. We are about to journey into that breath, into the pause between creation and illumination, into the universe's longest, quietest night. When we think of darkness, we think of absence. A room with the lights turned off, a forest path at midnight, the space between stars when you look up at a clear sky far from city lights. But these are not true darkness. These are merely places where light has not yet arrived, or where it has been blocked by something opaque. True darkness is different. True darkness is a place where light cannot exist at all, where the conditions for illumination have not yet been met. The cosmic dark age was not dark because someone turned off a switch. It was dark because the universe had not yet invented the mechanism for sustained light. The Big Bang had created photons, vast seas of them, more photons than atoms, more light particles than matter particles. But these photons were trapped. They would burst into existence, travel a microscopic distance, perhaps the width of a human hair, and then collide with an electron and be absorbed. Then they would be re-emitted, travel another hair's width, and be absorbed again. This cycle repeated trillions upon trillions of times every second, in every cubic inch of space. The photons existed, but they did not travel. They did not illuminate. They did not cast shadows. Imagine standing in a room filled with fog so thick that you cannot see your own hand in front of your face. The light is there. It is being produced by a lamp somewhere in the room, but it cannot reach your eyes because it keeps scattering off the tiny water droplets suspended in the air. Now imagine that the room is infinite, and the fog is made not of water but of free electrons. And instead of a lamp, there is only the residual heat of creation itself, slowly cooling. This is closer to what the cosmic dark age was like. Not absence of light, but imprisonment of light. Not emptiness, but a kind of fullness so complete that nothing could move through it. The universe was opaque. To understand why shadows were impossible, we need to understand what a shadow is. A shadow is the absence of light caused by an object blocking photons from reaching a surface. But in the cosmic dark age, there were no objects, no surfaces, and photons were not traveling in straight lines. They were not traveling at all in any meaningful sense. They were ping-ponging through space, colliding with electrons billions of times per second, never making any progress, never reaching anywhere new. An electron is a tiny, negatively charged particle. Photons, which are particles of light, interact very strongly with electrons. When a photon encounters an electron, it can be absorbed and re-emitted in a random direction. In the early universe, space was filled with free electrons, electrons that were not bound to atoms, just drifting freely through space. This meant that every photon was constantly colliding with electrons, being absorbed and re-emitted in an endless chaotic dance. The universe was like a crowded train station where every passenger is trying to move in a different direction, and everyone keeps bumping into everyone else, and no one can make any progress toward the exit. The photons wanted to travel. Travel is what photons do, it is their nature, but they could not. They were stuck. And because they were stuck, the universe could not see itself. There was no perspective from which to observe, no vantage point, no witness. In this sense, the cosmic dark age was not just a time when the universe was dark. It was a time when the concept of vision itself had no meaning. And then, slowly, over hundreds of thousands of years, something changed. The universe was expanding, and as it expanded, it cooled. Temperature is a measure of how fast particles are moving. The hotter something is, the faster its particles jiggle and vibrate. As the universe expanded and cooled, the free electrons and protons that filled space began to slow down. And as they slowed down, something extraordinary happened. They began to stick together. A proton is a positively charged particle, and an electron is negatively charged. Opposite charges attract. When a proton and an electron come close enough together, and when they are moving slowly enough, they can bind to each other and form a hydrogen atom. This process is called recombination. Although the name is somewhat misleading, it suggests that the proton and electron are combining again, but in fact this was the first time they had ever been bound together. Before this moment, they had been too hot, moving too fast, too energetic to settle into a stable partnership. But as the universe cooled, recombination became possible. When electrons became bound into atoms, something remarkable happened to the photons. They stopped colliding with them, or more precisely, they collided far less frequently. Bound electrons, electrons that are part of atoms, interact much less strongly with photons than free electrons do. It is a bit like the difference between trying to push someone who is standing on ice and trying to push someone who is anchored to the ground. The free electron is easy to jostle. The bound electron is much harder to disturb. And so, 380,000 years after the Big Bang, the universe became transparent. The fog cleared. Photons could suddenly travel freely through space without constantly being absorbed and re-emitted. For the first time, light could go somewhere, could cross vast distances. It could, in principle, reach an eye if any eyes had existed. This moment is sometimes called the surface of last scattering. It is the moment when photons stopped scattering off electrons and started traveling in straight lines. And the photons that were released at that moment are still traveling today. We can detect them with our instruments. They have been stretched by the expansion of the universe, redshifted from visible light into microwave radiation. But they are still here, filling space, a faint afterglow of the moment the universe became transparent. This is the cosmic microwave background, the baby picture of the universe, the snapshot of the instant when the fog lifted. But here is the crucial point. When the fog lifted, the universe was still dark. The electrons had stopped blocking the light, yes. Photons could travel freely, yes. But there were no sources of new light. The residual glow from the Big Bang was fading, redshifting away into the infrared and beyond. And there were no stars yet. No galaxies. No quasars. Nothing burning. The universe had become transparent just in time to see nothing. When recombination ended and the universe became transparent, space was filled with hydrogen gas. Neutral hydrogen atoms, each one consisting of a single proton orbited by a single electron. This gas was not evenly distributed. There were slight variations in density, tiny ripples left over from quantum fluctuations in the first moments after the Big Bang, but for the most part, it was extraordinarily uniform. Smooth, featureless, boring, if you can call the raw material of creation boring. The hydrogen drifted through space, slowly cooling as the universe expanded. It had no temperature gradient to speak of. Everywhere was roughly the same temperature, a few thousand degrees Kelvin, hot by human standards but cold by cosmic standards. The gas glowed faintly with infrared radiation, the leftover heat of the Big Bang slowly radiating away into the expanding void. But this glow was not visible light. It was not the kind of light that illuminates. It was merely the thermal signature of cooling matter, like the warmth you can feel radiating from a stove that has been turned off but has not yet cooled completely. If you could somehow have existed in this era, floating in space in some impossible vessel, you would have seen nothing. Absolutely nothing. No stars, no galaxies, no structure of any kind. Just darkness in every direction. And yet, paradoxically, you would have been surrounded by atoms. You would be immersed in an ocean of hydrogen, billions upon billions of atoms in every cubic meter of space. But they would emit no light. They would reflect no light. They would simply be there, invisible, filling the universe with their silent presence. This is one of the strangest aspects of the cosmic dark age. It was not empty, it was full. But fullness without light is indistinguishable from emptiness, at least to the eye. The hydrogen waited. That is the only word that seems appropriate, even though waiting implies intention, and gas has no intentions. But there is a patience to the way matter behaves when gravity is weak. The hydrogen atoms drifted through space, their paths determined by the slight variations in density left over from the early universe. In regions where the gas was slightly denser, gravity was slightly stronger, and the gas began to fall inward, slowly, almost imperceptibly, toward the center of those dense regions. This process is called gravitational collapse, but in the cosmic dark age, it did not feel like collapse. It felt like drift, like sedimentation, like sand slowly settling to the bottom of a jar of water. The time scales were enormous. Millions of years would pass with almost no visible change. The gas would compress slightly. The dense regions would become slightly denser. The voids, regions where the gas was thinner, would become slightly emptier. But nothing dramatic happened. No explosions. No sudden events. Just slow, patient contraction under the gentle but relentless pull of gravity. And during this time, the universe continued to expand. The space between the collapsing regions grew larger. The distance between the future sites of galaxies increased. If you could have watched from outside, the universe would have looked like a foam, with dense regions slowly separating from each other, connected by filaments of gas, surrounded by vast empty voids. This structure, the cosmic web, was already beginning to form, but it was forming in darkness. Invisibly, silently, the universe was building its architecture in the dark. There is a character in this story that we have not yet introduced, and it is the most important character of all. It is called dark matter, and it makes up most of the mass in the universe. We do not know what dark matter is made of. We cannot see it, cannot touch it, cannot detect it directly with any instrument we have built. But we know it is there because we can see its gravitational effects. We can see the way it bends light. We can measure the way it holds galaxies together. We can observe the way it shaped the distribution of matter in the early universe. In the cosmic dark age, dark matter was doing the heavy lifting. Literally, the hydrogen gas we have been describing, the visible matter, the atoms, was important, but it was not the main gravitational player. Dark matter was. Dark matter does not interact with light at all. It does not emit photons, does not absorb photons, does not scatter photons. It is invisible not because it is too dim to see, but because it simply does not participate in the electromagnetic interaction. It only participates in gravity, and gravity in the cosmic dark age was everything. The dark matter had begun collapsing before the hydrogen did. While the hydrogen was still hot and ionized, bouncing around with high energy, the dark matter was already falling inward, pulled by its own gravity, forming the seeds of future galaxies. By the time recombination happened and the universe became transparent, the dark matter had already created deep gravitational wells, regions of space where the gravitational pull was stronger than average. And when the hydrogen finally cooled enough to stop bouncing around so energetically, it began to fall into these wells. The dark matter was the invisible scaffolding. The hydrogen was the visible material. And together, they were building the structures that would eventually become galaxies. But they were building them slowly, in the dark, with no way to know what they were creating. It is a strange thing to consider. The universe was constructing its future without being able to see it, without light to reveal the work in progress. It was like a sculptor working in a pitch-black room, shaping clay by touch alone, with no way to step back and observe the emerging form. And yet the sculpture was taking shape. The gas was collapsing. The structures were forming. The seeds of galaxies were being planted, but they had not yet sprouted. There is a number in physics, a threshold density, that determines whether a cloud of hydrogen gas will collapse all the way down into a star or whether it will simply drift apart. This number is called the Jeans mass, after the physicist James Jeans, who first calculated it. If a cloud of gas has more mass than the Jeans mass, gravity will overcome the internal pressure of the gas, and the cloud will collapse. If the cloud has less than the Jeans mass, the pressure will win, and the cloud will expand or stay diffuse. In the cosmic dark age, most regions of space had less than the Jeans mass. The hydrogen was too spread out, too diffuse, too warm, could not collapse. Or rather, it could collapse slowly but not catastrophically, not fast enough to create stars. The gas would drift inward toward the dense regions, but the process was glacial. Millions of years would pass, tens of millions, and still no stars. But in the densest regions, in the very centers of the gravitational wells created by dark matter, something different was happening. The gas was compressing, and as it compressed, it heated up. This might seem counterintuitive. We usually think of compression as cooling, like the way a refrigerator works, but in gases, compression causes heating. When you squeeze gas into a smaller volume, the atoms collide with each other more frequently, and those collisions convert gravitational potential energy into kinetic energy, into heat. So as the hydrogen fell inward, deeper and deeper into the gravitational wells, it began to warm up. Not much at first, just a few degrees. But over millions of years, as more gas fell in, as the density increased, the temperature began to rise more noticeably. 100 degrees, 1,000 degrees, 10,000 degrees, and then something crucial happened. The gas became dense enough and hot enough that a new process could begin. A process that would change everything. Nuclear fusion. Nuclear fusion is the process by which atomic nuclei combine to form heavier nuclei, releasing energy in the process. In the core of a collapsing hydrogen cloud, when the density and temperature reach a certain threshold, hydrogen nuclei, protons, begin to collide with enough energy to overcome their mutual electrical repulsion and fuse together. For protons can fuse through a series of steps to form a helium nucleus. And when they do, a tiny amount of mass is converted into energy according to Einstein's equation, E equals mc squared. This energy is released as light, as heat, as radiation. The first star ignited. We do not know exactly when this happened. Our best estimates place it somewhere between 100 million and 200 million years after the Big Bang. We do not know where it happened or what the star looked like. It is lost to us now. That first star vanished into the deep past, its light so redshifted by the expansion of the universe that it is beyond the reach of even our most powerful telescopes. But we know it happened because we exist, because the universe is filled with stars now, and those stars had to come from somewhere. There had to be a first one. Imagine the moment. For 100 million years, the universe had been dark, silent, patient, and then, in one tiny region of space, in the core of a collapsing hydrogen cloud, the temperature crossed the threshold. Protons began to fuse. Energy began to pour out. And for the first time since the Big Bang, a sustained source of light appeared. The first star was not like the sun. It was much, much larger. Perhaps 100 times the mass of the sun, perhaps even more. The first stars were giants because they formed from pristine hydrogen, with no heavier elements to complicate the chemistry. And large stars burn hot and bright and fast. This first star would have shone with the light of 1,000,000 suns, blazing ferociously in the darkness, burning through its fuel in just a few million years. But before it burned out, it did something extraordinary. It illuminated the universe around it. For the first time in 100 million years, photons were traveling freely through space, not as the fading afterglow of the Big Bang, but as new light, fresh light generated by nuclear fusion. The star cast its light outward in all directions, and that light traveled through the hydrogen gas, revealing it, ionizing it, heating it. The universe was waking up. One star was not enough to end the cosmic dark age, but one star could trigger more stars. The light from the first star heated the gas around it, causing it to glow. This glow was not visible light. It was ultraviolet radiation, invisible to human eyes, but it was energetic enough to ionize hydrogen atoms, stripping the electrons away from the protons. This created expanding bubbles of ionized gas around each star. And here is the crucial part. Ionized gas cools more efficiently than neutral gas. When hydrogen is ionized, it can radiate energy more effectively, which means it can collapse more easily. So the light from the first stars actually helped the next generation of stars to form. Each star created conditions that made it easier for more stars to form nearby. This is called positive feedback, and it led to a cascade. One star became two, two became four, four became hundreds, hundreds became thousands, and as more stars ignited, more light filled the universe, and the bubbles of ionized gas grew larger and began to overlap. The cosmic dark age was ending, not all at once, but in stages, in phases. as the universe transitioned from complete darkness to a faint glow to a growing brightness. This period, the transition between the Dark Age and the fully illuminated universe, is called the Epoch of Reionization. It lasted for hundreds of millions of years. It was not a sharp boundary but a gradual shift, a dawn that took longer than all of human history to complete. But eventually it did complete. The last pockets of neutral hydrogen were ionized. The last shadows disappeared. The universe became fully transparent, fully lit, fully visible to itself. And from that point forward, the cosmos has been a place of light. During the cosmic dark age, structures were forming that would never be directly visible. Not just dark matter structures, those are always invisible, but structures in the distribution of gas, in the flow patterns of matter, in the seeds of what would become vast cosmic filaments and voids. These structures were being sculpted by gravity in the darkness, and by the time the first light appeared, they were already mature, already in place. This is one of the profound lessons of the cosmic dark age. Not everything that is important is visible. Not everything that shapes the future can be witnessed in the present. The architecture of the universe was built in the dark, and we only see the finished product, illuminated after the fact. Consider the cosmic web. Today, when we map the distribution of galaxies across the universe, we see a remarkable pattern. Galaxies are not distributed randomly. They cluster together along vast filaments, like beads on strings, separated by enormous voids where almost no galaxies exist. This structure, the cosmic web, looks like a three-dimensional spiderweb stretching across the observable universe. But this structure did not form after the first stars ignited. It formed before. During the Dark Age, the gas was already flowing along the filaments, already collapsing into the nodes where the filaments intersected, already avoiding the voids. By the time light appeared, the cosmic web was already there, waiting to be revealed. It is as if the universe had built a city in the dark, and when the lights finally came on, we could see the streets and buildings that had been constructed in silence. There is something humbling about the cosmic dark age. It reminds us that there are eras of history we can never fully observe, never fully reconstruct, because the information has been lost. Light carries information. When light from a distant object reaches us, it tells us about the conditions at the source, the temperature, the composition, the motion. But during the Dark Age, there was no light carrying information across vast distances. There were no distant observers, no signals, no messages. We can infer what the Dark Age was like using physics and computer simulations. We can model the behavior of gas and dark matter under gravity. We can calculate how long it would take for structures to form, how the temperature would evolve, when the first stars would ignite. And our models match the indirect evidence we have, the patterns in the cosmic microwave background, the distribution of galaxies, the chemical composition of old stars. But we cannot see the Dark Age directly. We cannot take a photograph of it. We cannot observe a specific cloud of gas collapsing in a specific location and say, "This is where the first star formed." The light from that era has been redshifted beyond detectability. It is too faint, too far away, too diluted by the expansion of the universe. There is a horizon to our knowledge, a limit to how far back we can see. And the cosmic dark age lies just beyond that limit, hidden from view, knowable only through inference and theory. This is not a flaw in our instruments or a failure of our science. It is a fundamental feature of the universe. Some things are inherently unobservable. Some eras of history leave no direct record. And yet they happened. They shaped everything that came after. They built the foundation upon which the visible universe rests. The Dark Age is a reminder that absence of evidence is not evidence of absence. That silence does not mean nothing happened. That darkness does not mean emptiness. If there is one quality that defines the cosmic Dark Age, it is patience. The universe was in no hurry. It had time. It had endless, incomprehensible expanses of time. And it used that time to build slowly, carefully, layer by layer, the structures that would eventually give rise to galaxies, stars, planets, and life. There is something almost meditative about this. The universe did not rush. It did not take shortcuts. It allowed gravity to work at its own pace, allowed matter to collapse as slowly as it needed to, allowed the first stars to form when the conditions were finally right. It waited 100 million years for the first ignition, and it would wait billions more for the first planets, and billions after that for the first life. From a human perspective, these timescales are paralyzing. We struggle to conceive of 1,000,000 years, let alone 100 million. Our civilizations rise and fall in mere thousands of years. Our individual lives last decades. The idea of waiting 100 million years for something to happen is beyond our capacity to genuinely feel. But the universe is not in a hurry. It does not experience impatience. It simply unfolds according to the laws of physics, one moment at a time, with no sense of urgency, no anxiety about the future, no regret about the past. And there is something calming in that, something restful. The universe's patience is a kind of permission to slow down, permission to let things develop at their own pace, permission to trust that the important things will happen when they are ready to happen, and not before. We tend to think of darkness as the absence of something valuable, the absence of light, the absence of sight, the absence of knowledge. But the cosmic dark age suggests a different perspective. Darkness is not merely absence. It is a state in its own right, a condition with its own qualities and possibilities. During the Dark Age, the universe was not stagnant. It was not frozen. It was actively constructing the structures that would define its future appearance. The darkness was a period of preparation, of foundation laying, of hidden work. It was necessary. Without the Dark Age, without that 100 million years of patient collapse, the first stars might never have formed at all. Darkness, in this sense, is productive. It is the space in which things gestate, in which structures take shape before they are revealed. It is the unseen labor that makes the visible possible. This has implications beyond cosmology. In our own lives, we experience periods of darkness, times when we cannot see the path forward, when progress feels invisible, when effort seems to produce no results. These periods can be frustrating, disorienting, difficult to endure. But the cosmic dark age reminds us that important work can happen in darkness, that structures can be built even when we cannot see them taking shape, that patience and persistence, even in the absence of immediate feedback, can lead to eventual ignition. The first star did not appear because the universe rushed. It appeared because the universe waited long enough for the conditions to be right. Another lesson from the Dark Age is the value of what cannot be seen. Dark matter, the invisible scaffolding that shaped the distribution of galaxies, is arguably more important than visible matter in determining the large-scale structure of the universe. It makes up 85% of the total mass, and yet we have never directly detected a single particle of it. This is a profound reminder that visibility and importance are not the same thing. Some of the most crucial elements of reality are invisible. Forces, fields, patterns, relationships. These things shape the world but cannot be seen directly. They must be inferred, intuited, understood through their effects rather than through direct observation. In human contexts, this is equally true. The most important aspects of a person's character, their intentions, their values, their inner experience, are invisible. We see behavior, but we do not see the thoughts and feelings that produce behavior. We see outcomes, but we do not see the processes that led to those outcomes. And yet, the invisible aspects are often more fundamental than the visible ones. The cosmic dark age teaches us to respect invisibility, to recognize that what we cannot see may be just as real, just as important as what we can see. Finally, the dark age is a story about emergence, about how new phenomena arise from simple initial conditions. The universe began with almost nothing, just hydrogen, helium, a slight variation in density, and the laws of physics. No stars, no complexity, no diversity, just uniformity and silence. But from that simplicity, complexity emerged. Gravity took the smooth distribution of gas and amplified the tiny variations, turning them into dense clumps. Those clumps collapsed further, heating up, until they crossed the threshold for fusion. And fusion created new elements, new chemistry, new possibilities. Stars produced carbon, oxygen, iron. Those elements were scattered into space when the stars exploded. New stars formed from the enriched gas with planets around them. And on at least one of those planets, chemistry became biology. All of this emerged from the darkness, from the patient, invisible work of gravity acting on hydrogen gas. The cosmic dark age was the beginning of a chain of emergence that led, eventually, to us. This is perhaps the most hopeful message of the dark age. That even from the simplest, darkest, most featureless beginning, extraordinary complexity can arise. That the universe has a tendency to create, to build, to diversify, to bring forth new forms of order and beauty. The first star was just the beginning. After it came galaxies, nebulae, planetary systems, oceans, forests, mines, all of it traceable back to that moment of ignition, when the darkness finally broke and the universe saw itself for the first time. But none of it would have been possible without the silence that came before, without the long, patient wait in the dark, without the hidden structures slowly forming, unseen and unwitnessed, in the cold emptiness of the early cosmos. The cosmic dark age lasted 100 million years. In cosmic terms, this is brief, a blink, a held breath. The universe is now 13.8 billion years old, which means the dark age occupied less than 1% of its total history. And yet that brief period was crucial. It was the bridge between the formless, uniform state of the early universe and the rich, structured cosmos we inhabit today. We live now in a universe of light, a universe where stars shine in every galaxy, where photons travel freely across billions of light years, where telescopes can peer back through time and observe the faint glow of ancient events. But we are the descendants of darkness. We are made of atoms forged in stars, and those stars only exist because of the patient collapse that happened in the dark. The cosmic dark age is over. It ended billions of years ago, when the first generation of stars ignited and began to fill the universe with light. But in a sense, the memory of that darkness remains. It is encoded in the structure of the universe, in the distribution of galaxies, in the patterns of the cosmic web. The darkness shaped the light. The silence gave birth to sound. The invisible made the visible possible. And so, as we drift toward sleep, we can reflect on this. On the fact that darkness is not the enemy of light, but its precursor. That patience is not the absence of progress, but the foundation of eventual transformation. That the most important work often happens out of sight, in the quiet spaces, in the times when nothing seems to be happening. The universe waited 100 million years for the first sunrise. And when that sunrise came, it was worth the wait. Sleep now, knowing that the darkness you rest in is not empty, not meaningless, not wasted. It is the space where hidden structures form, where energy gathers, where the next moment of ignition prepares itself in silence. The first stars have already ignited. The universe is awake. But the lesson of the cosmic dark age remains, that before every dawn, there is a night. And that night is not an obstacle to be endured, but a necessary passage. A time of quiet preparation, a darkness that holds within it all the light to come. Rest now, let the shadows gather, let the silence settle, and when you wake, the stars will still be shining, as they have for billions of years, carrying forward the light that was born from darkness, the illumination that emerged from the longest, quietest night the universe has ever known. Astronomers classify stars into populations based on their chemical composition. Population 1 stars, like our Sun, are rich in heavy elements: carbon, oxygen, iron, all the elements heavier than hydrogen and helium. These stars formed recently, in cosmic terms, from gas that had been enriched by previous generations of stars. Population 2 stars are older, formed from less enriched gas, and contain fewer heavy elements. But there is a third category, a hypothetical category, because we have never directly observed one. Population 3, the first stars. Stars made from pure primordial gas with no heavy elements at all. These stars were monsters. Without heavy elements, the gas clouds that formed the first stars could not cool efficiently. Heavy elements like carbon and oxygen are excellent at radiating away heat, which allows gas clouds to collapse into smaller, cooler stars. But primordial gas, composed only of hydrogen and helium, could not cool as effectively. This meant that the first gas clouds had to be much more massive before they could collapse all the way down to stellar densities. The result was that the first stars were enormous. Estimates suggest they were anywhere from 50 to several hundred times the mass of the Sun. A star with 100 solar masses is not just a bigger version of the Sun. It is a fundamentally different kind of object. It burns its fuel millions of times faster. Its core reaches temperatures of hundreds of millions of degrees, hot enough to fuse hydrogen into helium at an astonishing rate. Its surface glows with ultraviolet radiation so intense that it would sterilize any planet within 100 light-years. And it lives for only a few million years before exhausting its fuel and dying in a catastrophic explosion. These first giants were blue, intensely, brilliantly blue. Their surface temperatures exceeded 30,000 degrees Kelvin, compared to the Sun's modest 6,000 degrees. If you could somehow have stood near one of these stars, protected by some impossible shielding, you would not have seen it as a discrete object. You would have been blinded by the flood of ultraviolet light, your retinas overwhelmed, your skin ionized. The star would have been less like a lamp and more like a nuclear detonation frozen in time, pouring out energy at a rate that defies human comprehension. And yet, despite their violence, these stars were also fragile. Their immense mass meant that the pressure at their cores was enormous, driving fusion reactions at a runaway pace. They burned through their hydrogen in a few million years, then moved on to helium, then carbon, then oxygen, climbing the periodic table as each fuel source exhausted itself. The process was relentless, inevitable. The star had no way to slow down, no mechanism to moderate its energy output. It was locked into a trajectory that could only end one way, in collapse. When a massive star exhausts its nuclear fuel, the core can no longer support itself against gravity. The outer layers of the star fall inward, compressing the core to unimaginable densities, and then rebound in a supernova explosion that releases more energy in a few seconds than the Sun will emit in its entire 10 billion-year lifetime. The first supernovae were different from the supernovae we observe today. They were more energetic, more violent, because the stars that produced them were so much more massive. Some of these explosions may have been so powerful that they did not leave behind a neutron star or black hole remnant. Instead, they completely destroyed the star, blowing it apart and scattering its material across hundreds of light-years of space. These are called parent stability supernovae, and they represent the ultimate fate of the most massive population 3 stars. When these stars exploded, they did something extraordinary. They seeded the universe with the first heavy elements. Inside the cores of these giant stars, fusion had created carbon, oxygen, silicon, iron elements that had not existed in the universe before. And when the stars exploded, those elements were ejected into space, mixing with the pristine hydrogen and helium gas, enriching it, changing its chemistry. This was the beginning of cosmic chemical evolution. The first stars died so that the second generation of stars could be different, could be smaller, could form planets, could eventually give rise to life. It is a kind of cosmic sacrifice, although the word implies intention where there was none. The first stars did not choose to die. They simply followed the laws of physics, burning their fuel until there was nothing left to burn, and then collapsing under their own weight. But the effect was the same. They gave their substance to the universe. They transformed simple matter into complex matter. They made the future possible. The material ejected by a supernova does not travel slowly. It races outward at speeds of tens of thousands of kilometers per second, crashing into the surrounding gas like a shockwave, compressing it, heating it, stirring it. This creates turbulence, chaos. The smooth, uniform distribution of gas that existed during the cosmic dark age was disrupted by the first supernovae, broken up into a more complex, more interesting structure. And this turbulence had consequences. It triggered new star formation. When the shockwave from a supernova compresses a nearby gas cloud, it can push that cloud over the threshold for gravitational collapse, causing a new generation of stars to form. This is called triggered star formation, and it may have been one of the primary mechanisms by which the first galaxies assembled themselves. Each supernova triggered more stars. Those stars lived, burned, died, and triggered even more stars. The process was self-sustaining, self-amplifying. What began as a handful of isolated giants became a cascade of stellar births, each generation building on the chemical legacy of the previous one. And as the heavy elements accumulated, the nature of star formation changed. The second generation of stars, formed from gas enriched by supernova ejecta, were smaller than the first generation. They could cool more efficiently, collapse into lower mass configurations, live longer. They were more like the sun, and some of them perhaps had planets. The ultraviolet light from the first stars did not just illuminate the universe. It ionized it. Ultraviolet photons are energetic enough to strip electrons away from hydrogen atoms, turning neutral hydrogen into ionized hydrogen. And ionized hydrogen behaves differently from neutral hydrogen. It is more transparent to light, can radiate energy more efficiently. It responds differently to shock waves and pressure. This ionization feedback had a profound effect on star formation. In regions where the gas was already dense, ionization helped stars form by allowing the gas to cool and collapse. But in regions where the gas was more diffuse, ionization actually suppressed star formation by heating the gas and preventing it from collapsing. This created a kind of selection effect, where stars preferentially formed in the densest regions and avoided the voids. Over time, as more and more stars formed, the ionized regions grew and merged. The bubbles of ionized gas surrounding each star expanded, overlapped, and eventually filled the entire universe. This process, the epoch of reionization, transformed the universe from a mostly neutral state to a mostly ionized state. It was the second great transition after the first transition, recombination, that ended the initial fog of the Big Bang. But unlike recombination, which happened smoothly and uniformly across the universe, reionization happened in patches, in stages. Some regions were ionized early, when the first stars formed. Other regions remained neutral for hundreds of millions of years longer, until enough stars had formed nearby to ionize them. The universe became a patchwork of ionized and neutral regions, a complex mosaic that gradually shifted toward full ionization. By the time reionization was complete, about 1 billion years after the Big Bang, the universe looked nothing like it had during the cosmic dark age. It was filled with light, with structure, with diversity. The long silence had given way to a growing symphony. Galaxies did not form all at once. They formed hierarchically through a process of mergers and accretion. Small structures formed first, clumps of gas and dark matter, a few million times the mass of the sun. These clumps collapsed, formed stars, and then collided with neighboring clumps. The collisions caused them to merge, creating larger structures. These larger structures collided with other large structures, creating even larger ones. And so on, in a cascade of mergers that gradually assembled the massive galaxies we see today. This process is still happening. The Milky Way is currently in the process of colliding with the Andromeda Galaxy, and in a few billion years they will merge to form a single, larger galaxy. But the pace of mergers was much faster in the early universe, when galaxies were closer together and collisions were more frequent. The first billion years of cosmic history were a chaotic, violent time, full of collisions, mergers, and rapid growth. The galaxies that formed during this era were small and irregular. They did not have the grand spiral arms or smooth elliptical shapes of modern galaxies. They were clumpy, asymmetric, dominated by intense bursts of star formation. Observations from the James Webb Space Telescope have revealed these early galaxies in stunning detail, showing us just how different the young universe was from the universe we inhabit now. But even these small, irregular galaxies contained multitudes. They contained millions of stars, vast clouds of gas, intricate magnetic fields, and the seeds of future black holes. They were the building blocks of everything that would come later. Star formation in the early universe was not a smooth, continuous process. It happened in bursts. A region of gas would collapse, form a cluster of stars, and then those stars would explode as supernovae, blowing the remaining gas out of the region and temporarily halting star formation. This is called feedback, and it played a crucial role in regulating how galaxies grew. Without feedback, galaxies would have converted all of their gas into stars very quickly, leaving nothing behind for future generations. But feedback ensured that some gas remained, that star formation happened in waves rather than all at once. This gave galaxies time to grow, to accumulate more gas from their surroundings, to build up their mass gradually. Feedback also enriched the intergalactic medium, the diffuse gas between galaxies with heavy elements. When supernovae exploded, they ejected enriched material not just into the surrounding galaxy, but sometimes out of the galaxy entirely, into the vast spaces between galaxies. At the centers of the first galaxies, something else was forming: black holes. We do not fully understand how the first black holes formed, but we have several theories. One possibility is that they were the remnants of the first massive stars. When a star with more than about 25 solar masses dies, its core collapses directly into a black hole without rebounding in a supernova. These stellar mass black holes, perhaps a few tens of solar masses each, could have been the seeds that eventually grew into the supermassive black holes we observe at the centers of galaxies today. Another possibility is that black holes formed directly from collapsing gas clouds, without an intermediate stellar phase. In the densest regions of the early universe, where gas was collapsing rapidly and turbulently, it is possible that some clouds collapsed so fast that they bypassed star formation entirely and collapsed straight into black holes. These would have been more massive than stellar remnant black holes, perhaps thousands or even tens of thousands of solar masses, and could have grown more quickly into supermassive black holes. However they formed, black holes played a crucial role in shaping galaxies. As gas fell into a black hole, it heated up and radiated energy, sometimes more energy than an entire galaxy full of stars. This radiation could ionize gas, drive powerful winds, and even halt star formation in the surrounding region. Black holes, in other words, provided another form of feedback, another mechanism by which galaxies regulated their own growth. The relationship between black holes and galaxies is one of the most fascinating and least understood aspects of modern astrophysics. We observe that the mass of a galaxy's central black hole is tightly correlated with the mass of the galaxy's bulge, the dense, spherical region of stars at the galaxy's center. This suggests that black holes and galaxies grow together, influencing each other's evolution in ways we are still trying to understand. But in the early universe, this relationship was just beginning to form. The first black holes were small, growing slowly, accreting gas from their surroundings. Over billions of years, they would grow into the massive objects we observe today, weighing millions or billions of solar masses. But during the epoch of reionization, they were young, just beginning their long journey toward dominance. The universe began with almost no chemical complexity. Hydrogen, helium, trace amounts of lithium, that was it. 3 elements out of the 92 naturally occurring elements we know today. Everything else, carbon, oxygen, nitrogen, phosphorus, iron, gold, uranium, was created later, inside stars, through nuclear fusion and supernova explosions. This process is called nucleosynthesis, and it is the reason the periodic table exists. Each element has its own origin story, its own formation mechanism. Carbon is created in the cores of medium-sized stars through the triple alpha process, where 3 helium nuclei fuse together. Oxygen is created in more massive stars. Iron is created in the final moments before a supernova, as the star's core collapses and rebounds. Elements heavier than iron, gold, platinum, uranium are created in the unimaginably violent environment of neutron star mergers, where the density and temperature are high enough to build up atomic nuclei through rapid neutron capture. The first stars began this process. They created the first carbon, the first oxygen, the first iron. And when they died, they scattered those elements into space, seeding the universe with chemical diversity. The second generation of stars inherited this legacy, incorporated these elements into their own structures, and added to them. The third generation did the same, and so on, through billions of years, as the universe slowly transformed from a place of elemental simplicity to a place of chemical richness. Today, the gas clouds from which stars form contain about 2% heavy elements by mass. That might not sound like much, but it is enough to fundamentally change how stars and planets form. Heavy elements allow gas to cool more efficiently, which allows smaller stars to form. They provide the raw material for rocky planets, for liquid water, for organic chemistry. They make life possible. And all of this complexity emerged from the deaths of stars, from the violent, explosive endings of objects that existed for only a few million years, billions of years ago, in a universe that was still learning how to shine. There is a cycle at work here, a grand cycle of matter and energy that has been running for over 13 billion years. Gas collapses into stars. Stars fuse light elements into heavy elements. Stars die, scattering those elements into space. The enriched gas collapses into new stars. The cycle repeats. This cycle is not closed. Some gas is locked up in stars that live longer than the current age of the universe. Some gas is ejected into intergalactic space and never returns. Some matter falls into black holes and is removed from the cycle entirely. But the cycle continues regardless, processing the universe's hydrogen supply, slowly but steadily, into heavier and heavier elements. Our sun is a product of this cycle. It formed from gas enriched by countless previous generations of stars. The carbon in our bodies, the oxygen we breathe, the calcium in our bones. All of it was forged in stars that lived and died before our solar system even existed. We are, quite literally, made of stardust. This is not a poetic metaphor. It is a sober statement of fact. And the cycle will continue long after we are gone. The sun will eventually die, gently puffing off its outer layers into space, enriching the interstellar medium with the helium it has spent billions of years creating. That material will be incorporated into future stars, future planets, perhaps even future forms of life. The atoms that currently make up your body will be scattered and recycled, reused, woven into new structures, new patterns, new configurations. Nothing is wasted. Nothing is lost. Everything is transformed. Some elements are much rarer than others. Gold, for example, is extraordinarily rare. It is created only in neutron star mergers, which are themselves rare events. The gold in a wedding ring represents material that was created in one of the most violent events in the universe, in a collision that lasted only a few seconds but released more energy than the sun will emit in its entire lifetime. This rarity has consequences. It means that planets rich in heavy elements are relatively rare, at least in the early universe. It means that the conditions necessary for complex chemistry, conditions that require a diverse palette of elements, took time to develop. The universe had to wait for multiple generations of stars to live and die before enough heavy elements accumulated for rocky planets to form. Earth is made possible by this long history of stellar death. We orbit a third-generation star, formed from gas that has been processed multiple times through the nuclear furnaces of previous stars. The iron in Earth's core, the silicon in its crust, the oxygen in its atmosphere. All of it is recycled material, forged in stars that died billions of years ago. And this raises a profound question. How common is this? How many other planets have been enriched by stellar alchemy to the point where life can emerge? We do not yet know. The chemical composition of exoplanets is difficult to measure, and we have only just begun to survey the diversity of planetary systems in our galaxy. But the fact that we exist, that Earth exists, suggests that the process is not impossibly rare. It happened at least once. And if it happened once, it might have happened many times. The cosmic dark age, in this sense, was not just a prelude to stars. It was a prelude to chemistry, to planets, to life. It was the beginning of a chain of events that led, through billions of years of stellar death and rebirth, to the emergence of complexity, of consciousness, of observers capable of looking back at the darkness and wondering what it was like. There is a quality to deep time that resists comprehension. Our minds are not built to grasp spans of millions or billions of years. We can say the numbers, 100 million years, 13 billion years, but we cannot feel them. They remain abstract, intellectual, disconnected from our lived experience. And yet, there is value in trying, in sitting with the enormity of cosmic time, in allowing ourselves to feel, however faintly, the weight of those incomprehensible spans. Because deep time teaches us something important about perspective, about patience, about the nature of change. Consider again the cosmic dark age. 100 million years. During that time, nothing visible happened. No stars formed. No light appeared. Just slow, patient gravitational collapse, invisible, incremental, building toward an eventual threshold. From a human perspective, this looks like stagnation, like nothing. But from a cosmic perspective, it was essential. It was the foundation. Without it, nothing that came after would have been possible. This has relevance to our own lives. We live in a culture that values speed, immediate results, visible progress. We expect transformation to happen quickly, dramatically, on timescales we can perceive and control. But the cosmic dark age reminds us that the most important transformations often happen slowly, invisibly, over timescales that dwarf our own lifetimes. Trees grow for decades before they bear fruit. Mountains are built by tectonic forces that take millions of years to move continents. Species evolve over spans of time that make human history look like a blink. And the universe itself waited 100 million years in darkness before the first star could shine. There is wisdom in this slowness, a kind of deep patience that is not passive, not resigned, but active and creative. The patience of seeds germinating underground. The patience of ice slowly carving canyons. The patience of the universe building its own architecture in the dark. In our daily lives, we are often anxious about time. We worry that we are not progressing fast enough, not achieving enough, not transforming quickly enough. We compare ourselves to others who seem to be moving faster, accomplishing more. We feel the pressure of deadlines, of expectations, of the relentless ticking of the clock. But the cosmos does not feel this pressure. It moves at its own pace, indifferent to our sense of urgency. And there is something comforting in that, something restful. The universe is not anxious. It does not rush. It simply unfolds moment by moment, according to the laws of physics, with no concern for whether the process is fast or slow, efficient or meandering. The cosmic dark age was not a failure. It was not a delay. It was exactly as long as it needed to be. The first stars formed when the conditions were right, and not a moment sooner. And the universe did not suffer from their absence. It did not pine for light. It simply existed in darkness until darkness gave way to dawn. We could learn from this. We could allow ourselves to move at our own pace, to trust that transformation will happen when the conditions are right and not before. We could release the anxiety of comparison, the fear of falling behind, the belief that slowness is a form of failure. The universe waited 100 million years, and it was fine. There is another layer to this meditation, a more personal layer. Each of us carries within us periods of darkness, times when we cannot see clearly, when progress feels invisible, when we are waiting for something to ignite but do not know when or how it will happen. These periods can be frightening. They can feel like failure, like stagnation, like being stuck in a place from which we will never escape. But the cosmic dark age offers a different perspective. It suggests that darkness is not the absence of progress, but a different kind of progress. A hidden internal progress. The building of invisible structures that will eventually support visible transformation. During the cosmic dark age, the universe was not empty. It was not idle. It was actively constructing the architecture that would give rise to stars, galaxies, and all the complexity that followed. The darkness was productive. It was necessary. It was the space in which the future was being prepared. Perhaps our own periods of darkness are similar. Perhaps they are not wastes of time but essential phases of growth. Periods during which invisible structures are forming. Internal foundations are being laid. Energy is gathering in preparation for eventual ignition. Perhaps the darkness is not something to escape from but something to trust, to sit with, to allow to do its work. This does not mean that darkness is easy. It does not mean that waiting is painless. But it does mean that darkness has meaning, that it is part of the process, that even when we cannot see what is happening, something important may be taking shape. The first stars emerged from darkness, and so perhaps will we. The cosmic dark age ended billions of years ago. The first stars ignited, lived briefly, and died, scattering the seeds of future complexity across the universe. More stars formed, more galaxies assembled, and over time the cosmos transformed from a dark, uniform void into the rich, structured, luminous place we observe today. We are the inheritors of this process. We exist because the cosmic dark age happened, because the first stars formed and died, because the cycle of stellar birth and death enriched the universe with the elements necessary for planets and life. We are not separate from this history. We are embedded in it. We are made of it. Every atom in your body is a relic of cosmic history. The hydrogen in your water was formed in the first minutes after the Big Bang. The carbon in your cells was forged in the core of a dying star. The oxygen you breathe was created in a supernova explosion. You are a collection of stardust, a temporary configuration of atoms that have been cycling through the universe for billions of years and will continue to cycle for billions more after you are gone. This is not a diminishment. It is an enlargement. It means that you are connected to everything, to the stars, to the galaxies, to the darkness that came before the light. You are part of the cosmic story, not as an observer but as a participant, as a piece of the universe becoming aware of itself. And the darkness, the cosmic dark age, the 100 million years of silence, is part of your inheritance too. It is part of what made you possible. Without it, without that patient, invisible collapse, the stars would not have formed, the elements would not have been created, and the chain of events that led to your existence would never have begun. So as you settle into sleep, as you allow your own consciousness to dim and drift, you can reflect on this. On the fact that darkness is not your enemy, that silence is not emptiness, that the invisible work of rest and patience and slow transformation is just as real, just as important, as the visible work of action and achievement. The universe rested in darkness for 100 million years, and when it emerged from that darkness, it shone with a light that has not dimmed in 13 billion years. You too can rest. You too can trust the darkness. You too can allow the hidden structures within you to form, quietly, invisibly, without rush or pressure. And when the time is right, when the conditions are met, you will ignite. You will shine. Not because you forced it, not because you rushed it, but because you allowed it to unfold in its own time at its own pace. The first stars are still shining, even the ones that died billions of years ago. Their light has been transformed, scattered, recycled, but it has never disappeared. Energy cannot be destroyed, only changed. And so the light from the first stars lives on in new stars, in new forms, in new configurations. And so will you. Long after this moment has passed, long after this particular configuration of atoms has dispersed, the energy that animates you will continue. It will be transformed, yes, but it will not vanish. It will flow forward, as light flows forward, as the universe flows forward, carrying the memory of the darkness from which it came. Rest now. Let the silence settle. Let the darkness gather. You are part of an ancient process, a cosmic cycle of rest and awakening, of darkness and light, of collapse and ignition that has been unfolding since the beginning of time. The stars are waiting. The universe is patient. And when you wake, the light will still be there, as it has always been, shining forward from that first impossible moment when darkness broke and the cosmos saw itself for the very first time. Sleep well. The universe is holding you, and it has all the time in the world.